Okay, so welcome to Moses' Data Clinic. In this video, we are discussing Physics 5124 and Physics 5054, and the topic we are discussing is on turning effects of forces and equilibrium. So we are discussing turning effects of forces and we are discussing equilibrium. Then both these concepts have to do with the center of mass. But before we go into our discussion of these concepts, we'll start with discussing turning effects, most commonly known as moments of a force. So the first thing that we need to understand before we go to equilibrium and center of mass is the concept of a moment of a force. So the first question that we ask ourselves is, what is a moment or a turning effect? So when you see the word turning effect or moment of a force, it's just the same thing. So the definition of a moment is, it's the product of a force and the perpendicular distance from the pivot at which that force is acting. So in this definition, they've just written down the formula. Moment is equal to force times perpendicular distance from pivot. So this times this multiplication, we just call it a product. So a moment is a product of a force and the perpendicular distance from the pivot of action of that force. Now the units for moments are Newton meters. So it's just N for newtons, small m for meters. So those are the units for a moment. The definition again, a turning effect or a moment is the product of a force and the perpendicular distance from the pivot of action of that force. Now, these moments or these turning effects are categorized into two classes. There are moments that are known as clockwise moments, and then there are moments that are known as anti-clockwise moments. So let's look at this diagram here to help us understand more about clockwise and anti-clockwise moments. So we have this figure here. There is this lever, then it's tied here. There is that hinge, so that's our turning point. Then we've got a cylinder. Inside this cylinder there are some materials that we are trying to crush. So in order for us to crush these materials, we have to pull this lever downwards. But as we pull that lever downwards, the materials inside the cylinder exert an upward force on the plunger. So now, what moments are being produced? Let's start with the moment as a result of this 20 Newton force. So this 20 Newton is a force that's acting on this lever and it's making it turn at this hinge. So we've got the first moment, which is this 120 Newton multiplied by this distance of the lever from the hinge. And then when we look at the direction in which this lever arm will turn, if we pull it downwards, it's going to turn in that direction, or in other words, it will go in the anti-clockwise direction. Then when we look at this other force, it's acting on the lever arm at this point. If it were the only force, it would cause the lever arm to turn at this hinge in that direction. So we've got two moments. This moment making the lever turn in that direction, and that moment making the lever turn in that direction. So this is known as the anti-clockwise direction. Then this other direction is known as the clockwise direction. So that's how we determine the direction or the category of a particular moment, whether it's clockwise or anti-clockwise. And that's the important thing that I want us to get from this diagram, just identifying how to know the direction of a moment. So every time that we are given a problem on moments, first and foremost, we should be able to identify which ones are clockwise and which ones are anti-clockwise. So a clockwise moment is that moment that causes a lever or an arm to turn in the clockwise direction. That's a clockwise moment. Then an anti-clockwise moment is a moment that causes the lever to turn in an anti-clockwise direction. Then how to remember clockwise and anti-clockwise? We draw a circle, then we put two arrows at the beginning and at the end. So the arrow going from left, this arrow that's going from left to right, this is the anti-clockwise direction. And then we have this other arrow going from right to left, that is the clockwise direction. So when we are dealing with moments, we should be able to identify the clockwise moments and the anti-clockwise moments. And then apart from identifying the clockwise and anti-clockwise moments, we should also be able to identify what is known as the pivot or the fulcrum. So this pivot or fulcrum is just the point at which the object rotates. So every time we are solving questions on moments, we pay attention to three things. Which ones are the clockwise moments? Which ones are the anti-clockwise moments? And where is our pivot? So if we are able to identify those three things in any given scenario, then we won't have any problem solving questions on moments. Like in this particular scenario, the 20 Newton force is causing an anti-clockwise moment. The force from the crushed material is causing a clockwise moment, and this point labeled H, that is our pivot. So in any question that's dealing with moments, if we are able to identify the clockwise moments, the anti-clockwise moments, and the pivot, then believe you me, we've already done 50% of all the work that needs to be done in order for us to be able to solve that particular problem. So apart from identifying the clockwise moments, the anti-clockwise moments, and the pivots, there are just two more theories that we need to know. Then our theory on moments is done, and all we have to do is look at examples. So those two theories are, first of all, the theory of equilibrium. So first of all, the theory of equilibrium, and then the other theory is the principle of moments. So the theory of equilibrium simply tells us that for an object that is in equilibrium, there is no resultant force. I'll say that again. For an object that is in equilibrium, there is no resultant force. This is our theory of equilibrium. Then the other theory that we need to know is the principle of moments. So the principle of moments states that for an object in equilibrium, the sum of the clockwise moments about any point is equal to the sum of the anticlockwise moments about the same point. So don't worry about this statement talking about any point and the same point. This point is simply the pivot or the fulcrum. So the principle of moments, in other words, you can state it as for an object in equilibrium, the sum of the clockwise moments about any pivot is equal to the sum of the anticlockwise moments about the same pivot. So clockwise moments, anticlockwise moments, pivot or fulcrum, equilibrium, and the principle of moments. If we are comfortable with those 5 theories, then well and good. All we have to do now is look at a few examples. Now, what will be happening is when we are solving past examination questions and we are trying to look at the type of questions that we may encounter in our exams, those questions are most likely to look like this. They might look like this scenario here, or they might look like a different scenario. Where are we? Okay, or they might look like this scenario here. So we're going to start with the first scenario, our first example. It says figure 3.1 shows a uniform iron bar. So this is our uniform iron bar. Then it has a weight of 30 newtons. We can see the weight has been shown there. It's 30 newtons. And it has a length of 1.4 meters. The bar is being used to lift one edge of a concrete slab. This is our concrete slab. Then a stone placed 0.2 meters from one end, this is our stone, acts as a pivot. And then a force of 40 newtons, this is our force, pushing down at this end is just enough to lift this slab and hold it, like we can see in this entire scenario. So now what we want to do is to just show that this arrangement is in equilibrium. Now remember, I said before we go to center of mass, we first have to discuss moments, which we have discussed. Now when we talk about center of mass, it's important in identifying the particular point on an object where its weight acts. So the center of mass is the point on an object where its entire weight is concentrated, or where its entire weight acts. Then when you see the word uniform, it's usually uniform iron bar or uniform meter rule. And this is the only scenario that we are given. We are always given uniform bars, uniform meter rules, and so on and so forth. Nevertheless, when we see the phrase uniform, we should just know automatically that the center of mass is in the middle. Okay, so that's what this statement is telling us about. The weight of the bar acts through the center of mass. And where is that center of mass? Because it's a uniform bar, the center of mass is in the middle. Now, how do we calculate this middle? The entire distance of the bar is 1.4 meters. So if we cut this 1.4 meters in between, we'll have our 1.4 divided by 2, and it will give us 0.7 meters. So the center of mass of this uniform bar is at 0.7 meters. Okay, so as we have seen in the diagram, the center of mass here is at 0.7 meters, or at the center of the bar. Now we want to check whether this object is in equilibrium. So what do? We have to identify the clockwise moments and the anti-clockwise moments. So we look at the forces that are acting in this scenario. First and foremost, we have this 40 Newton force acting in this direction, which is clockwise. Then we have the weight of the iron bar, which is a 30 Newton force. It's also acting in this direction, which is clockwise. Then we have the force that's lifting the concrete slab, like that. We have our first force, the 40 Newton, that's the clockwise direction. We have our second force, the 30 Newton, which is the mass of the iron bar through the center of mass, that's in a clockwise direction as well. And then we have the third force, the force holding up this concrete slab, and this force is in the anti-clockwise direction. So now we want to see whether this object is in equilibrium. Then for an object to be in equilibrium, the sum of the clockwise moments should be equal to the sum of the anti-clockwise moments. So let's start with our clockwise moments. And this is the first scenario, clockwise moments on the bar. And which ones are our clockwise moments? We have the force we have the moment due to that 40 Newton force, and we have the moment due to this 30 Newton force. And where are those forces acting? At the pivot. So we have the center of mass, we have the 40 newtons. Where are they making this object turn? At the pivot. What's a moment? It's the force multiplied by distance from the pivot. For this other 30 Newton, we also have force multiplied by distance from the pivot. And that's the working that has been done here. For our 30 Newton force, its distance from the pivot is 0.5 meters. Remember, this 30 Newton is in the center of the iron bar. So it's half of 1.4, which is 0.7. So from this end to the center, the entire length is 0.7 meters. But the moment of this 30 Newton force is acting with respect to the lever. So that moment will be the 30 Newton force multiplied by the distance of that force from the pivot, or it's acting with respect to the pivot. So the moment of the 30 Newton force will be the magnitude of the force, which is 30 newtons, multiplied by its distance from the pivot. Now, from the center to the end, we have 0.7. From the pivot to the end, we have 0.2. So from the pivot to the center, we have 0.7 minus 0.2, which is that 0.5 meters that we can see there. That's what's happening. I'll just say that again. So we have from the center of mass to the end of our iron bar, the length is 0.7. From the center to the end, the length is 0.7. Then from the pivot to the end, the length is 0.2, which means from the pivot to the center, we have 0.7 minus 0.2, which will give us that 0.5 there. So the moment due to this 30 Newton force will be 30 Newton multiplied by 0.5 meters, which is its distance from the pivot. And that's our first calculation we have. So that's our 30 Newton multiplied by 0.5 meters. That's one of our clockwise moments. We have another clockwise moment, which is the moment due to the 40 Newton force. So the distance from the pivot to the 40 Newton force will be 1.4 minus 0.2, which will give us this 1.2 meters that we're able to see there. The distance from the 40 Newton force, which is at this end, to the pivot, which is there, is going to be 1.4 meters minus 0.2 meters, and that will give us 1.2 meters. So the moment due to the 40 Newton force is going to be that 40 Newton multiplied by 1.2 meters. So these are our two clockwise moments. We have this one, 30 newtons multiplied by 0.5 meters, and we have this other force, 40 newtons multiplied by 1.2 meters. So when we add all the clockwise moments, we find that the sum of the clockwise moments is 63 Newton meters. So that's the sum of our clockwise moments, which are the moment due to the 40 Newton force and the moment due to the weight of the iron bar. Then we go to the anti-clockwise moments. So for the anti-clockwise moments, we only have one force. For the anti-clockwise moments, we only have the force that's holding the slab away from the ground. So that clockwise moment is this force holding the slab, then it's 0.2 meters away from the pivot. So the moment due to the slab, or the moment of the force holding up the slab, will be this force multiplied by 0.2. So this would be our anti-clockwise moments, and there's only one. Now, because this object is in equilibrium and we have found that the clockwise moment is 63 Newton meters, it means even our anti-clockwise moment must be equal to 63. So whatever force we have, if we multiply it by 0.2, it should give us 63. And in order for us to find the value of F, we divide by 0.2 on both sides, and we can see there we remain with F is equal to 63 divided by 0.2, like we can see there. Therefore, the force holding up the slab is 315 newtons. So, like I said, if we are able to identify clockwise moments and anti-clockwise moments, and we are able to see and we are able to understand equilibrium and the principle of moments, then we've done all the work that we need to do when it comes to solving problems involving moments. So this is our introduction to moments. Then in our next video, we will look at 3 examples of problems on moments and how to approach them. However, the key is understanding what was happening here. These calculations. Understanding that these were our clockwise moments, and because the object is in equilibrium, the sum of the clockwise must be equal to the anti-clockwise. This was our anti-clockwise, so it should also be equal to the clockwise. And by using that principle, we are able to find the value of the unknown force which was holding up the slab. So below are some examples of applications of moments of forces. So moments are used in spanners, scissors, in taps, nutcrackers, in seesaws, especially in seesaws, and so on and so forth. So this is our video on the principle of moments. Then after this video, the next one is looking at examples of examination past questions that deal with moments and how to approach those problems. Stay tuned.